I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
Welcome to Introduction to the Moon. This is the first lecture in the Moon 101 series, and it's designed to give you a brief overview of a lot of different subjects about the moon that other lecturers will go into in more detail in the successive lectures. My name is Dean Epler. I'm a retired NASA lunar geologist, and I'm presenting this material, although it was originally put together by Paul Spudis, the scientist who originated the whole Moon 101 concept about 10 years ago. Paul has passed away, and I'm trying to fill in for him, hopefully in such a way that he will not be disappointed. So the first important part that we need to discuss is really what the moon is. And the real key, I think, is that the moon is a planet. It has many of the features that we think of as a planet, as in having a core, having a mantle, having a crust. No other planet is as proportionally large as the moon is with respect to the size of the Earth. Many of the other planetary bodies that have moons, such as Mars, have small irregular moons that seem to be just sort of accidentally captured into the orbit of their primary body. The moon has a heavily cratered surface. It is partially flooded by lava flows, which erupted somewhere between 4 billion and about 1 billion years ago, with the bulk of the lava being emplaced around 4 to 2.2 billion years ago. Since the moon has formed, there have been many impacts by comets and asteroids, and they have radically altered the outer surface of the moon. It has created what is a chaotic upper layer of debris, which we call regolith, and it has deeply fractured the lunar crust to a depth of over 10 kilometers. By and large, the moon was a dead planet by about 1 billion years ago. There's a lot we don't know about the history of the moon, and some of these unknown items are key to understanding the history of the Earth-Moon system. The moon is covered by a particulate blanket, and I say particulate blanket because it is really a mix of particle sizes all the way from extremely tiny sizes all the way up to boulders that are the size of a building. It is easily accessed. It is a likely feedstock for resource extraction. And if you look at the picture of John Young's feet, this picture was taken on Apollo 16, you'll see that there is actually fluffy dirt regolith kicked up around it. And it gives you a nature of how loose and fluffy the upper layer of the regolith is. But in the upper right corner, you see the picture of an extremely small, but nevertheless almost perfect crystal of a mineral. The moon's regolith is full of things like this. As I said, it goes all the way from large rocks down to the finest fraction that you can imagine. I want to go into some general properties. On the left is the moon, in the center is Mars in red, and on the right is Earth in blue. And if you compare the numbers for any given variable across the graph, you're going to see that the moon and Mars are actually a lot more like each other than Mars is like the Earth. A lot of people have taken the view that Mars is more like the Earth, and to a certain extent, that's justified in light of what we think the early Martian history is now, in that we think it was warm and it was wet. But the size of the planet, its composition, its very nature makes it actually a lot more like the moon than it is like Earth. The moon has a history. Before Apollo, it was dubbed the Rosetta Stone of the planets. And after Apollo, in the immediate years after Apollo, a lot of people sort of wondered, well, was it really? But as time has gone on, and as we've analyzed lunar samples, we've come to believe that moniker, in fact, is absolutely correct. And much of what we understand now about the other planets in the solar system as well as the Earth. We've learned because the moon has preserved a history that many other planets no longer have. Now, before we went to the moon on Apollo with human beings, we had quite a bit of precursor missions from the United States. In addition to that, the Soviet program landed a considerable number of spacecraft on the surface, as well as flew vehicles around it. Before we could even think about landing on the moon, we had to understand what the moon was actually like on its surface. And it's really important to recognize that before these vehicles went to the moon, the smallest thing we had ever seen on the lunar surface through terrestrial telescopes was about 1 kilometer on a side. And the questions we had before we sent these spacecraft there seem somewhat silly now, but there were things like, where do craters run out? Are the craters all the way down to the smallest size? Are there rocks on the surface? Is the surface capable of bearing the weight of a lunar module? All of these things now we understand, perfectly well. But before we went to the moon with people on Apollo, we didn't know any of that. And this set of robotic missions clarified that. And I'm going to talk about each one in turn. The first successful spacecraft that basically touched the moon was the Ranger series. The Ranger series were hard landers in that they had no other, I suppose you could say, objectives other than hitting the surface and imaging the surface all the way down. As such, the only thing they did was photograph the surface. But this was really key because prior to the Ranger set of missions, we simply had no idea what the surface was like at a human scale. Ranger answered a tremendous number of questions that, frankly, we had had since Galileo first turned his telescope to the moon. There was a whole variety of soft landers, which, for obvious reasons, did a lot more when they got to the surface than the Ranger did. The Surveyor was an American mission. It flew 7 total spacecraft in the series, of which I believe 4 were successful. The whole purpose of the Surveyor missions was to safely soft land on the moon, to understand the nature of the lunar surface, and to do some basic chemical analysis. But largely it was, you can think of it as largely a civil engineering mission. What we wanted to know is, A, can we land on the moon? Is it possible to have a spacecraft, fly to the lunar surface and survive? The second thing is, what is the surface like? Is it soft? Is it a hard rock? What is it like? Is it like a snowbank that will disappear into? And the Surveyor was an incredibly successful set of missions that we're still analyzing data from. The Soviets, in addition, flew 3 sample return missions to the moon in the 70s. The Luna 16, 20, and 24 missions not only brought back samples from places we did not go on Apollo, they did it robotically. And at this point, no other country on the Earth has robotically recovered a sample from the lunar surface. In addition, the Soviets landed 2 Lunokhod rovers, which were incredibly successful. They drove around the moon's surface, again in places that the Apollo missions hadn't gone. And the 2 sets of Soviet missions greatly enhanced what we understood from Apollo by simply providing complementary samples from other places on the moon the Apollo program did not get to. Lastly, Lunar Orbiter was another really key mission because it circled the moon and photographed about 75% of the surface. At that, up to the point of the Lunar Orbiter missions, the only real global view of the moon that we had was from telescopic observations, and telescopic observations that simply do not see the lunar far side. Lunar Orbiter was a mapping mission. It was intended to collect global mapping data that the Apollo program could use in planning landings. Now recently, and I say recently within the last 10 years or so, we have been flying, not just we, the United States, but the human race has been flying a significant number of orbital missions around the moon. Countries that had never done this before, like China, Japan, India, have flown a number of really successful missions and again have enhanced our understanding of the moon's surface. In addition to that, The Chinese have landed a soft lander with a rover in a manner not dissimilar from the Lunokhod missions. Okay, the first mission I want to take a look at is Selene. This was flown by the Japanese Space Agency. It carried a variety of instruments on board with three general objectives. First was to photograph the surface. Before the Selene mission went, we did not have any better resolution of the surface than we had on Apollo. The Selene mission improved that considerably. In addition to that, it carried geochemical remote sensors, basically instruments that could look down at the surface and capture radiation that would tell us what the composition of the lunar surface was. And in addition to that, it carried instruments to look at the nature of space at the orbital altitude of the spacecraft. Chang'e 1 was a Chinese instrument and carried much or similar payloads and had similar goals to the Kaguya Selene mission. And it was doing essentially two big missions. One was to look at the lunar surface and to get good images and good altimetry. And the second was to collect remote sensing data on the composition of the surface as well. Chang'e 2 was similar to Chang'e 1, but it was primarily directed toward looking at the landing site for the Chang'e lander. So it was essentially a reconnaissance mission for a very specific spot on the lunar surface. Once it completed its mission, it left lunar orbit and went to the Earth Lagrange point 2, and then went from there on an asteroid expedition. So it was an extremely capable spacecraft, and it is still flying. Chandrayaan was a mission that was flown by the Indian Space Agency, but included payloads not only from the Indian Space Agency, but from the United Kingdom, from ESA, and from the United States as well. Again, collecting more and more detailed information about the lunar surface, similar in a way to the other satellites. Now, the first one that I think is really critical from the United States is something called GRAIL, Gravity Recovery and Interior Laboratory Mission. GRAIL was a spacecraft, or actually a pair of spacecraft, whose mission was to map out the lunar gravity field in incredible detail. And the idea behind this spacecraft was that the two co-orbiting spacecraft could determine the difference between themselves to an accuracy of about 1 micron. As that distance between the two spacecraft changed, that indicated that there was a change in the gravity field felt at orbit. And that in turn allowed us to do an incredibly detailed gravity map of the moon. Once it got its primary mission done at a particularly high altitude, they stepped the orbit down and got increasingly detailed data at lower and lower altitudes until, in fact, the spacecraft ran into the surface. Because the moon's gravity field is unusual, it's lumpy, we tend not to fly spacecraft close to the moon early on in a mission because it's very easy to have the spacecraft impact. So many spacecraft will be flown at a higher altitude initially and then flown lower once we have a good data set. Another specific mission flown by the United States was a spacecraft called LADEE. Several times in the course of the Apollo program, we thought we may have seen particulate materials high in lunar orbit, and that remained a mystery as to what actually the high altitude environment was, particularly with respect to lunar dust. And the LADEE mission was flown to essentially look for lunar dust and to understand the nature of that high altitude environment. Lastly, and perhaps the most successful of all the missions, is the Lunar Reconnaissance Orbiter. Lunar Reconnaissance Orbiter was flown initially in the Constellation program, and essentially what it was doing was collecting all the data we felt we needed to plug holes in both the lunar map and our concept of global variations in things like topography and composition. LRO was originally planned to be a 1 to 2 mission. It is still in orbit. It's been there for 8 years, and it has returned some of the most phenomenally accurate and detailed photographs of the lunar surface that have ever been recovered. And they have changed many of the ways we think about the lunar surface. The only lander that has been on the surface since Apollo is the Chinese U-2 lander, which was carried to the surface as part of the Chang'e 3 spacecraft. It landed in Mare Imbrium, about 40 kilometers southwest from a crater called Laplace F, and it operated for approximately 2 lunar days on the surface. It was really important because it deployed to an area we did not go on Apollo, and in addition to that, it deployed instruments that we simply didn't even have during Apollo, such as a ground-penetrating radar. And it has returned data that is revolutionary, and it was a magnificent mission. So I want to talk about some gross properties of the moon. And it's always important to start with what the moon looks like, both from the Earth and that part which we mostly cannot see, and that's the lunar far side. The moon has presented a variable face to humankind. Specifically, it's got dark and light areas. And the variations in albedo, the reflected light, whether they're bright or dark, it turns out tell us some very important things about the moon that we now know because of the various spacecraft that have been there. This is a series of lunar globes that look at 3 different elements: thorium, titanium, and iron. And I want to look at these in great detail, but one of the things I need everybody to recognize from this is that the albedo, the change in the gray tone of the lunar surface, actually maps very nicely to composition. This is the iron map of a goodly portion of the moon, and the variations range from brighter, warmer colors as higher iron and cooler, darker colors as less iron. Now, if you look at the moon in plain light, like we see the moon when we look up at it, you can see that the higher, brighter colors on the iron map correspond to the darker areas on the moon. And that's because the darker areas on the moon are filled with lava flows, and lavas are basaltic in composition, the same kind of rocks you see in Hawaii, and they tend to be higher in iron than the lighter color rocks on the rest of the moon. So we can see from that composition reflects albedo. Now, if we look at the titanium map, we see something very similar, although there are some variations in this. Not all basalts are alike. Some basalts have higher titanium, some basalts have lower titanium. The color scheme is the same as the iron map. Brighter colors have higher, lower colors have lower titanium. And you can see that not all the dark areas of the moon, the lavas, have the same titanium composition. We essentially discovered that from Apollo, from return samples. And we were lucky before we even knew this that we picked sites that coincidentally turned out to be places that had variations in titanium. But again, you can see on the western side of the moon and on sort of the central eastern side, we have a lot of titanium. In much of the rest of the moon, we don't have much titanium. Lastly, if we look at thorium, we see, again, the darker areas of the moon having a lot of thorium, and thorium is a radioactive element, and it's indicative of sort of evolved magmas that have spent a lot more time cooking, and that will be discussed in a later lecture. But again, if you go back to the picture of the moon that we see from the Earth, you can see that the concentrations of thorium match many of the colors that we also see on the lunar surface. In this case, they map to some place that we call the Procellarum creep terrain, where creep, K-R-E-P, stands for potassium, rare earth elements, and phosphorus. Let's talk about the lunar surface environment, and there's really 4 parameters that I think are really important. One is temperature and sunlight. The 2 are paired, and the other 2 are hydrogen content and what you can see of the Earth and how easy it is to communicate. The temperature on the moon really divides the moon into 2 different regimes. One is polar, which are colder, just like the Earth, and the other is the nonpolar environments, where, depending on where the sun is, it'd be hot or cold, just like the Earth. At noon, we get the hottest temperatures. On the moon, at noon, we get the hottest temperatures. When the sun goes down on most of the moon, it gets quite cold at night. The poles, on the other hand, are colder, but the temperature is much more stable than it is on the rest of the moon. Let's talk a little bit about hydrogen content. Hydrogen is a really critical element for essentially living off the moon. You can combine it with oxygen to make water. You can use it as rocket fuel. So where the hydrogen is really important. The nonpolar portions of the moon, the hydrogen ranges from as low as 10 parts per million to as many as 90 parts per million. The poles, however, we're pretty sure that the hydrogen content on average is greater than 150 parts per million, and it's why the poles remain an attractive target for lunar settlement. Lastly, direct-to-Earth communications. The moon is in locked rotation with the Earth, and that means that basically wherever you are in the lunar near side, the Earth will be in sight and it'll always stay in the same place. At the poles, the Earth is really low to the horizon. If the terrain isn't in the way, you can see it all the time, much as you do from the front side. But there are many times when the terrain may block it. The lunar far side never sees the Earth. So if you're going to operate on the lunar far side and you want to talk to the Earth, you're going to need a continuous relay satellite. So let's talk in more detail about thermal conditions, because the temperature is what we're going to have to work in when we're on the lunar surface. Nighttime surfaces are very cold, down to as cold as 150 degrees centigrade. And noontime temperatures are equally high, about 100 degrees centigrade. Polar areas are either always dark or have grazing solar incidence. So there are areas that we refer to as the permanently shadowed areas. These areas are extremely cold. In fact, many people have estimated that these are the coldest places in the solar system. The permanently shadowed areas on the moon never see the sun and probably have not seen the sun for hundreds of millions of years. Consequently, they are extremely cold, down to 50 to 70 degrees Kelvin. Another critical part of the lunar environment is micrometeorites. First, there's no atmosphere to impede the impact of all debris, so the speed at which, or the velocity at which it's coming in from space around the moon is not attenuated at all as it is on the Earth. There's a variable flux. I'm not going to repeat all the numbers on the graph there, but basically the smaller the object, the more there are of them. A lot of surface rocks have craters that are on the order of 1 to 10 microns. That's the size of the crater. In many cases, the damage from the impact extends far away from that actual crater, and it creates something we call zap pits. The Apollo astronauts noticed zap pits on the surface rocks, and once the rocks were back, it turns out that it becomes a very useful piece of data as to how long a rock's been sitting on the lunar surface and whether it's been tumbled. In other words, does it have the same face always facing the sky, or has it been rolled around? If it hasn't been tumbled, the top surface will have a lot of zap pits, the undersurface won't. If it's been tumbled around, the undersurface will have zap pits. And it turned out we could actually determine how rocks were bouncing around on the lunar surface by looking at the zap pits. One critical part of the discussion of micrometeorites is that even though there's micrometeorites coming into the moon and they're not slowed down, the impact hazard on the lunar surface is estimated to be about 4 times less than in low Earth orbit. So the lunar surface environment is much safer in terms of micrometeorites than low Earth orbit, where International Space Station is. Now, the moon's orbit is pretty interesting. Like all bodies in the solar system, it's not in a circular orbit, it's in an elliptical orbit. And in this case, the perigee and apogee being the farthest it's away from the Earth and the perigee being the closest it is, vary by about 45,000 kilometers. One key part of the fact that the moon has an apogee and perigee is that the size of the moon is actually quite a bit different when it's as far away as it can get and as close as it can get. The one on the left is when the moon is as far away as it is from the Earth. The one on the right is its closest approach. And there is a considerable difference in the moon's size. So when you step out at night and look at a full moon and you think, gosh, that's a lot larger than I remember it being, sometime in the past, it's not an optical illusion. That's actually happening, and it's because the moon is in an elliptical orbit. There's something we call the barycenter, and that is the center, the point at which the entire system rotates, and that's about 1,700 kilometers below the Earth's surface. It is not at the center of the Earth because the moon is actually quite heavy relative to the Earth, so that center of rotation is actually displaced from the center of the Earth. The moon has an orbital period of about a month. We know this because every month we go through a new moon and we go through a full moon and then back to a new moon. It is not exactly a month long, so there are months that come along where you get 2 full moons in the month, and that's why. Okay, let's talk a little bit about the moon's orbit and eclipses. They could be more common if all of the orbital parameters of the Earth and moon lined up. Basically, what happens to get an eclipse is that at the point of new moon, in other words, when the moon is located between the Earth and the sun, it's directly on what we call the Earth-Sun line. That is the line that's drawn essentially between the center of the Earth and the center of the moon. Because the moon's orbital plane is different from the Earth, and because that plane precesses around the Earth because of tidal and gravitational forces, those 3 conditions, Earth-Sun line and the moon right in that Earth-Sun line, don't happen very often. And so it's a special case of a new moon. If all of those were aligned every month, we'd have an eclipse, but we're not so lucky. Let's talk a little bit about something we call libration. The moon wobbles around its axis, and it actually has what we call longitudinal and latitudinal axis. Longitudinal libration means it's basically wobbling back and forth on its elliptical plane. Latitudinal means it's wobbling back and forth on its essentially north-south line. Because of that, we can actually see slightly into the far side and the poles of the moon if we didn't have libration. So about 8 degrees beyond the 90-degree west and 90-degree east points, and about 6.5 degrees beyond the north and south polar. If you look at these 2 photographs that were taken at different parts in the year, on the left photograph, there's the crater Endymion pointed out, and you can't quite see it, but Mare Crisium is the black crater essentially at the center. If you look at the picture on the right, Endymion has now shifted to the left and more into view, and Mare Humboldtium, which normally we would not see, we can see. Likewise, Mare Crisium is no longer right on the limb, but is slightly tilted toward the Earth, and that's just libration at work. Topography is an important thing that geologists think about in terms of a planet's history and its conditions, because it tells us a lot about how strong the crust is and what's happening on the interior. We now have a really, really good idea of what the topography of the moon is like. The moon is bumpy. It has extremes in elevation from as low as 9 kilometers below an established altitude and as high as 8 kilometers above that. Now, we have pictures like this, and we use blue, cooler colors as the lower, and yellow, red, and white as the higher altitudes. But one of the things that's really key is that the moon has elevations extremes that are essentially the same as the Earth, from the seafloor to the mountains. There's a couple of things that I think are important to talk about. One is, of course, the lunar near side has the traditional thing we think of as the man in the moon patches of dark, but it turns out, of course, these are also where the moon is low, and that's consistent. Lava flows, when they erupt, flow into lower spots, and we know now that those lower spots are the remnants of very large impact craters from the early on in the lunar history. The lighter areas are what we call the highlands, in between the lower spots, and they're much elevated. Interestingly, if you look at the far side, on the lower part of the far side, we see this big dark blue area, and that's something called the South Pole Lake and Basin. That's generally acknowledged to be the largest impact crater in the solar system, and it's actually a pretty big hole on the moon, and we really didn't understand that it was there, although there were hints, until we had these kinds of maps more recently. In addition to the South Pole Aitken Basin, you can see at the equatorial part of the far side of the moon, we have our highest topography, again up to about 8 kilometers above the agreed on datum. The topography of the moon is largely bimodal. In other words, you're either on the rough, lighter colored highland areas or the smooth, darker colored Maria. When we consider roughness, we're really talking in most cases about whether it's mountainous or not mountainous. And those are big scale things in terms of the terrain. But it's also important to consider whether we have roughness at a human scale, or in the case of going back to the moon, on a lander scale. And the highland areas turn out to be actually smoother at a lander scale, and the Maria are rougher at the lander scale. Lunar landforms are dominated by cratering. We talk a little bit about lava flows, but even the lava flows are affected by cratering because the lava flows are found filling craters. There are literally thousands of impact craters, ranging from the size of the South Pole Aitken Basin, which is 2,500 kilometers across, to the zap hits, which are microns across. The shape and form of an individual crater changes as a result of two things. One is the size. The larger craters tend to be flatter floored. The smaller ones tend to be more bowl-shaped. In addition to that, as a crater spends time at the lunar surface, in other words, it goes from being a young crater to an older crater, it gets more and more subdued until finally it's just barely there. Unlike the Earth, the terrain on the moon is not dominated by plate tectonics process. It is solely a function of where things have impacted and the volcanic events that have filled those areas. In any event, completely smooth, flat areas on the moon are rare. They occur in the Maria, but the Maria are fairly old, so they have been broken by numerous craters as well. The slopes in the Maria are around 4 to 5 degrees on average, so it's not very, very steep terrain, although as you can see the crater in the center of this picture, if you get close to a young crater, the terrain gets quite a bit steeper. The Highland Maria boundary is generally sharp and abrupt, much as we see here at the Apollo 15 site in the Hadley-Apennine region. Because of that abruptness of the boundaries is again why we see the dark Maria areas. If those boundaries were not abrupt, the Maria would not have that sharp, obvious image on the moon's surface. The highland terrain consists largely of rolling hills, some of them quite high, but nevertheless not jagged, steep cliff faces like we see on terrestrial topographies. The highland terrains are created largely by overlapping ejecta blankets from large craters. If we get close to a young crater, for instance like Tycho, the terrain is quite rough. But away from the young impact craters, the average slopes are 7 to 10 degrees, but the scale of the topography at, let's say, a lander image or a lander footprint is quite smooth. Surface lighting is something that not only we dealt with on Apollo, both in terms of operating on the lunar surface, but also seeing the topography for crews to land at, but also we'll be worried about it when we go back to the moon because we're there to stay. Apollo 12 had the shallowest sun angles, so 7.5 to 9.5 degrees, very shallow. Apollo 16 had the highest sun angles, 45 to 48 degrees. On the left is an Apollo 12 picture on EVA-1. You can see how long the shadow of the lunar module and the astronaut is. On the right is the Apollo 16 site at the highest sun angle. And in contrast, the surface is much brighter, the shadows are smaller, and in general, it's harder to see your way around on the terrain in high sun angles than it is in lower sun angles. Anybody that's ever been skiing in flat light knows that you can ski off some remarkable terrain that you didn't even see because the shadows aren't there. In some ways, driving around on the moon in high sun angles is going to be similar to that, and possibly when you drive, you're going to have to be tacking back and forth down sun. These are two pictures essentially looking up sun and down sun. Apollo 12 EVA-1 down sun, the sun is 7.5 degrees. So you can see if you're looking directly down sun, you don't see much, but if you look to the right or to the left, you can see quite a bit. And that's what I mean about having to tack back and forth around the sun. If you want to make sure you don't drive into something that's exciting, you're going to have to be careful how you drive. In contrast, Apollo 17 EVA, sun's about 16 degrees, and that's looking up sun. The terrain is somewhat easier to see, but it's still glaring sunlight when you're going directly into the sun. A unique aspect of working on the lunar near side in the dark is illumination by earthshine. Because the moon's orbit is locked and we always see the same face of the moon, the Earth always stays in the same spot in the sky. And when you have a full Earth, it's something like 80 times brighter than a full moon. At essentially lunar midnight, if you're out working under the Earth with a full Earth, it's as bright as about 8 o'clock on a summer evening on the Earth. So the reality is that when you're out at night in Earthshine, you'll be able to see just about everything you need to without artificial illumination. John Young once told me that not only was it bright enough to see the lunar surface from orbit with Earthshine, you could actually tell color differences and see individual craters with Earthshine. So Earthshine is going to be an asset that's really important for future lunar operations, unless, of course, you're on the far side. The far side, the Earth is never in view. So when the sun goes down on the far side, with the exception of starlight, it's going to be really dark. In addition to that, when we're working at the poles, because the sun is so low to the horizon and the Earthshine is so low to the horizon, you're almost always going to need some level of illumination so you just don't step into dark holes because of the low sun angle. Let's talk about regolith. Regolith is one of those aspects of the lunar surface that has received a lot of discussion over the years. There will be a further lecture just on regolith, but I want to touch on it here to give you an idea of what it is. The basic definition of regolith, and this is a geologic definition, is the layer or mantle of loose, unconsolidated rock material of varied origin that rests on bedrock over most of the lunar surface. In other words, regolith is what happens if you take bedrock and just beat it up until it's just nothing but fragmental material. We use regolith on the Earth to talk about soils as well, but the moon is essentially just plain old rock. The regolith can be formed in place or it can be transported from adjacent locations. Generally speaking, if you pick up a handful of regolith at any one spot on the lunar surface, roughly 90% of the material in your hand is going to have been derived very locally. About 10% will have been transported in by meteorite impacts from other locations. There are a lot of processes that affect regolith formation. Obviously, the principal one that creates regolith is meteorite impact. It breaks up the bedrock into all sizes, and the variety and sizes of meteorites create variety and sizes of regolith. In addition to that, we have cosmic rays, we have solar wind, and those create variations in the regolith which have caused it to be quite different at a very, very small scale, and I'll leave that discussion to the subsequent lecture. The median particle size of regolith is about 40 to 130 microns. That's really small, and it's much smaller than we experience, for instance, when we're at the beach. 95% of the regolith is less than 1 millimeter, and if you're out the beach, the roughly average size of the sand is about 2 millimeters. So the moon is not going to be like a day at the beach. There are a lot of things in the regolith. There's a lot of things mixed up. It's ground broken rock, it's impact melt, it's bits and pieces of meteorites, so it's very variable. The graph shows the variation in the nature of the regolith at various landing sites, in this case surveyor landing sites. You don't need to take away real detailed specifics on this, but it's important to recognize that the regolith isn't the same all around the moon. As the surface gets older, in other words, it's been exposed to the lunar at the lunar surface for a longer period of time, it changes grain size, it changes character. So every landing site will be slightly different. When we landed the lunar modules on the regolith, we had a variety of essentially interactions between the regolith and the lunar module. First thing, of course, is everybody knows that down close to the surface, the astronauts saw dust moving around. And if you look at the upper left picture and the lower left picture, those are sort of striations, little ridges and troughs created in the regolith by the ejecta, by the exhaust from the lunar module. If you look at the upper right picture, you can see that in that case, the regolith was quite fluffy and the foot pad sank, probably 1 to 2 centimeters into the regolith. On the lower right picture, you can see that, in fact, the foot pad is just sitting on the regolith. So how compact and how fluffy the regolith varies from place to place. But none of it, in no place, is that fluffiness deeper than about 10 centimeters. There's been a lot of discussion about dust and what it does to astronauts and hardware and rovers and spacesuits and things like that. The picture is of Gene Cernan after EVA-3 on Apollo 17. He's just pulled his suit off, and you can see that he's got a lot of dirt on his face, not because the regolith came into the suit during his EVA, but because the suits, which you can see piled on the ascent engine cover in the background, were pretty dirty from walking around on the lunar surface. There's been a lot of discussion about levitated dust. There's been a lot of discussion about whether dust is a critical design issue that will cause failure if it's not followed or not paid attention to. Levitated dust has been suggested both by the horizon glow taken on the surveyor cameras and by photographs and notes made by Gene Cernan as the Apollo 17 command module approached the terminator. There's been a lot of discussion, is dust levitated? Does it move around on the lunar surface? There's a couple of things we can look at to try and get some idea of whether there is a large-scale transport of dust on the surface. The first is on Apollo 11, 14, and 15, we put laser retroreflectors on the surface. Now, these were corner cube reflectors that were designed to reflect laser light back to the Earth. So if there's dust moving around, you would really expect those corner cubes to get covered. And even if they're not completely covered, you would expect to see some reduction in the signal strength coming from the moon over time. The Apollo 11 retroreflector has been on the moon now for over 48 years. The others somewhat less time. There has been no evidence of any degradation in laser signal over the lifetime of these arrays. So if there's dust moving around, it's not covering the retroreflectors. When we went to the moon on Apollo 12, we landed near the Surveyor 3, which had spent 31 months on the lunar surface prior to the arrival of the Apollo 12 crew. Although there was some dust coating on parts, the patterns on the coating indicated that the dust was blown onto the Surveyor either by the lunar module landing or by the engines of the Surveyor itself. Again, there was no evidence of dust having settled on the spacecraft from any other source other than the engine exhaust. In fact, there was even a study published where a research team looked at the Surveyor parts brought back to the Earth, and they saw no evidence that dust was on these parts except by blown on by the engine bells. Now, when we establish an outpost, because engine bells do blow dust around, we're going to have to be careful about where we land our spacecraft so that we don't spray dust all over our habitats, deployed equipment, and instruments on the surface. So in that case, we will have to accommodate the fact that if you have an engine coming past the surface, it's going to blow dirt around. There's been some discussion also about whether dust is moving in the Terminator. When the Terminator comes by, there's some suggestion that there are variations in the electrical current, which some people have suggested would cause dust to levitate. So I want to talk a little bit about that particular issue as well. And this concern was raised before Apollo, and Apollo, I think, provides us some pretty conclusive proof that it's not happening. The first, I think, that's really important is that the albedo gradients between the highlands and the mare, the highland rocks being lighter colored, the mare rocks being darker colored, are sharp and distinct. They're preserved at remote sensing scales, they're preserved at photographic scales, and the crews on the surface could see them. In the upper right, or the right, is a picture of the Apollo 17 site. You can see very clearly that the highland terrains are distinct from the mare fill in the valley. At the left, you have a geologic map from a publication in 2002 that shows, by using remote sensing data, that those albedo variations indeed represent compositional variations, and that there is no sense that there's a homogenization of the lunar surface from dust. Likewise, if you go up to orbital altitudes and look at things like the mare highland boundaries, in this case Mare Crisium, on the left you see the albedo picture, on the right you see the iron map, and again, you can see clearly that iron does not bleed over into the highland terrain, that the boundaries, the albedo boundaries, are as sharp in the remote sensing data as they are in the visible light. LADEE was a spacecraft I talked a little about earlier as having been sent to the moon recently to look at whether there was a dust component in the high altitude lunar exosphere. And in fact, LADEE saw, while there was some tenuous dust, there was no evidence of electrostatically lost dust at high altitudes. Lastly, if a lot of dust was moving around, we would expect the rocks at the surface to be either covered in dust or at least have a mantle of dust. And there is no evidence on rocks that have been essentially exposed to the surface for hundreds of millions of years of any accumulated dust blanket. We conclude that lateral dust transport on the moon, if it happens at all, is very inefficient and is not coating the lunar surface with new dust every time the sunrise goes by. Let's talk briefly about the origin of the moon. We'll get into more detail in subsequent lectures, but there were three traditional modes that were advanced prior to Apollo. Some of these modes date back to literally Charles Darwin's grandfather. The first was what we call the fission model. The idea was that early on in the history of the Earth, when it was largely molten, and if it was rotating fast, mass dissimilarities would cause a bulge to be created, and you would essentially birth a moon from that mass distinction. Darwin's grandfather actually suggested that the Pacific Ocean was where that body came from. The second origin theory was that both the Earth and the Moon essentially accreted in the same spot, but created two different bodies, what we call co-accretion. And lastly, we thought that potentially the Moon was formed elsewhere in the solar system and was ultimately captured by the Earth when the Moon in a different orbit came nearby. We know for sure that the moons of Mars, for instance, were captured in such a way that they're actually asteroids which were forced out of the asteroid belt and were captured by Mars and are now permanent satellites. So one of the outcomes of the Apollo program was we discovered that these models are, for the most part, wrong. And we did that on the basis of understanding that the Moon had undergone a fairly violent early history, and by inference the Earth, and also by looking at similarities and differences between lunar samples and terrestrial rocks. After quite a few years, and I mean like a decade, more than a decade after Apollo, that length of time was necessary to really assimilate all the data and start to come up with new models of the formation of the Moon. And what is now called the giant impact hypothesis is the reigning model for the creation of the Moon. What we believe now is that very early in the solar system's history, in some cases no more than 10 to 15 million